Okay, back again. So we did number 2 in period 8. Number 3 now is a problem that I think I spent a fair amount of time on in period 1, maybe? I could be wrong. But let's go over this one. This one for sure has much more interesting functions. Both functions have restricted domains. Let's just do them right now. We know that we need to reference them. So what's the domain of function f? We know that for a log, the argument here always has to be greater than 0, strictly greater than 0. It can't be 0. So we'll still take -6 as our cutoff, but we won't include it, and we'll say that x has to always be greater than that. So there's our domain. Now with the radical, we know that the radicand has to always be greater than or equal to 0. So we'll take 3 as our cutoff, but we will include it, and we'll say x has to be always greater than that. So it's 3 to infinity. So without doing a lick of work, we should already know the domain of our sum function. It's going to be the intersection of these two sets. And if you are not certain what the intersection is, it's 3 to infinity. If you are not certain why it's 3 to infinity, then, one thing you could do, which hopefully you won't have to do too many times before you just start to understand intersections. But go ahead and draw a picture. Visual representations help. For the log function, we've got a -6 over here. And we said that our function is happy to accept anything bigger than that. So -6 itself is no good. But if you're bigger than -6, you're fine. On the other hand, our log function only wants values that are bigger than or equal to 3. So suddenly if you're 3, that's fine. You're included, so I'll make a dot. And you gotta be bigger. So seeing these two intervals like highlighted on a number line, we could overlap them. We're looking for what they share. It's pretty clear that the only thing they share is 3 and everything bigger than 3. So we could, there's no real reason to mark this, but we can show in orange that our intersection is actually exactly the same as the domain of G. Okay. So there, I'm not going to do that every time. What happened? Yeah, I should be able to select that. Delete. Delete. Even delete this answer too. I can't. Delete. Okay, now let's just do the problem. The algebra here is really basic because you can't simplify anything. So we know that our function rule is just literally going to be log base 2 of x plus 6 plus the square root of x minus 3. And you cannot simplify that, so you're done. And we already said the domain of f plus g is essentially just going to end up being the domain of function g, the 3 to infinity domain. So there you go. There's both of the things I wanted you to do. Function rule, domain. Next. Again, I meant to go to the difference function next, but I blew it somehow. So we'll do the quotient. That's fine. That's a more interesting question anyway, always. So in the numerator, we'll have the radical x minus 3. And the denominator will have the log looking good. Can't simplify it, so we'll box it up. Okay, now what's our domain? We know that it's still going to involve the intersection of the two sets, so that's 3 to infinity. But there should be an extra restriction down here, because if this log function was allowed to equal 0, we would have trouble. Mr. F blew it though, again. I'll explain why. When's this log function going to equal 0? We'd grab the whole log. Log base 2 of x plus 6. You'd set it equal to 0 and then we would solve. To solve logs, maybe some of you remember, that you take the log and you convert it to an exponential equation, because we know the meaning of a log is that it's equal to the power that you'd raise the base to get the argument. So this log expression directly translates into an equation where you're just taking 2, raising it to the power of 0, and that would equal x plus 6. So it's just not a log anymore. You just convert it using essentially the definition of what a logarithm is. Then 2 to the 0 is of course 1. Now you're just looking at a linear equation. Subtract 6, you get negative 5. Why is that bad? It's bad because negative 5 isn't even in our restricted domain anyway, right? So we went through all this rigmarole to find some other value that we potentially need to restrict from our domain, and it lies on the outside of our domain anyway. So there's no reason to restrict it. It's not in there. So if Mr. F wasn't a big dumb dummy, maybe we could have just changed this to minus. But we couldn't do that anyway, because if we change that to a minus, then our domain would have changed here. If we let this be a minus, then our domain would now be 6 to infinity, not including. This guy's domain would still be 3 to infinity. So the overlap here would now be the 6 to infinity. And then making that change from plus to minus, minus, minus. Maybe this is good. Maybe this does help. Because we add, we get 7. And suddenly, yeah, 7 now would be in that interval. And we would have to further restrict our domain so that it goes 6 to 7, not including 7, union 7 to infinity. So there's 2 ways that problem could have went. As written, we got a further restriction on our domain that wasn't even in the domain that we already had. So we didn't have to do anything extra. But if I left it at that, you guys might not have realized that in a slightly different situation, maybe the quotient function does generate another x that would have been in our interval and does need to be cut away. So this for sure is the better problem. If I had left this at a minus, this would have been a better, more interesting problem. So I hope you guys understand both sides of that coin. Kind of important that we do that, right? That we think about the special case that maybe we overlooked. But I'm now going to delete all that because it is not relevant to this question. It's all just addendum. I have a lot of addendums. Okay, so this is where we really are. And again, you're noticing that since that falls outside of our restricted domain anyway, we don't have to do anything about it. That's that. That's the final domain. Okay, let's do the difference. For the difference function, we're going to write function f first. Then we're going to write function g. Then we're going to put a minus sign between them. And then we're going to be done, because you can't simplify it all. Then for our domain, we're going to grab the exact same domain that we already used for the sum function, because sum, difference, and product function, they always have the same domains. They're just the intersection of the 2 domains, which for us has been 3 to infinity. Not a lot to do here for part C, so for once in my life, I'll try to keep it short and sweet and move on. All right, next quotient function, or should we do the product? Let's do the product, get it out of the way. For the product function, you're going to write log base 2 of x plus 6. Then you're going to write the radical, root x minus 3. Then you're going to put a multiplication sign between them. Then you're going to put a box around it because you can't simplify it anyway. Then when it comes to the domain, you're going to find the intersection of the 2 domains, which is the same domain as the sum and difference, like I just told you a second ago. So it's 3 to infinity. So very boring. Those questions were very boring. But now we can do this quotient. Maybe this one will be interesting. In the numerator, we want the log. So log base 2 of x plus 6. In the denominator, we want the radical, root x minus 3. And you don't need to try to simplify that. For your domain, well, the intersection of the two domains was 3 to infinity, including 3. But with a quotient function, we have that new restriction that says, hey, g of x must not be allowed to equal 0. And sort of obviously, the value of x that will make the denominator 0 is 3. 3 minus 3 would make 0. Normally that's fine. It's fine to have a 0 under the radical. But when that 0 turns into a 0 in the denominator, it's suddenly not okay anymore. So we make a tiny tweak to our domain, and it becomes 3 to infinity, but not including 3. And that tiny change is relevant. So make sure you understand that. Then, let's go to the two compositions. See how this changes things. So with function f as our outer function, we're getting log base 2 of x plus 6, where x really becomes the radical function, so root x minus 3. And we can't simplify that. So as far as function rules go, we're done. I guess I did say in class that I like the radicals to go to the end. So we could at least flip-flop this and say 6 plus root x minus 3. Okay. Then to come up with the domain, I guess with compositions you can just start with giving the domain of the function as written. For a log, you know that you want the thing in parentheses to always be greater than 0. But if you think this through the way I hope you will, you remember that root x minus 3, you know that graph. You know it's just a square root function that's been pushed 3 to the right. So what do you know about the outputs of that function? You can see that they're always positive. And we're adding 6 to them anyway. So they're always positive, and then they're greater than they used to be by 6. So are we ever in trouble of trying to take the log of a number that is negative? Why did it take me so long to get that out? Are we ever going to be taking the log of anything negative, or even 0? No. Because the range on this function is 0 to infinity, plus 6 is 6 to infinity. We're well clear of any restrictions on log. However, you can't just take the domain of the function as written. You have to also consider the domain of your inner function, which is the radical. So we're still going to inherit those restrictions from the radical. And even though this log function would be, sort of happy to accept other values, we can only use the values that are 3 or greater. And there you go. All right, what if we compose the other way? Then it's the root x minus 3. That becomes our outer function shell. The inner function is now the log base 2 of x plus 6. And again, there's no way to clean this up. No, just going to be log base 2 x plus 6 minus 3. I'm kind of lying, of course. There is a way to clean this up, but I'm not going to tell it to you because it's coming down the road. So there's no point in wasting time on it now. Leaving it like this would be fine. So what's our domain going to be? Well, I guess I said that we want to make sure that the thing we're taking the square root of is never negative. that means taking this entire log equation and trying to solve it. So that's what we're going to do. So we'll say that log base 2 of x plus 6 minus 3 must always be greater than or equal to 0. I'll add 3 to both sides and I'll get log base 2 of x plus 6 must always be greater than or equal to 3. I'm now staring down a log, I don't want to say equation because it's not one of those, it's a log inequality, but still our method of attack is the same. We know that we can convert this from logarithmic notation to exponential. Again, remember, log base 2 of x plus 6 and 3 means that 2 to the 3 would equal x plus 6. But this is an inequality. It's a little hairy as to how I do this. If this was an equation, then it wouldn't matter which stuff I put on which side. But with an inequality, it obviously does. We're saying that something over here is bigger than or less than what I put over here. So I know that what I want to do is have 2 to the 3 on one side and an x plus 6 on the other side. But who's supposed to be bigger, right? Who's supposed to be the bigger thing? And I'm literally not sure how to answer that exactly. I know what it should be, but how do I explain that? If we want this log to be bigger than 3, if the log is bigger than 3, I guess I'll just try to say it. If we want the log to be bigger, then we would want the stuff in parentheses to be bigger, bigger, bigger. I'm saying that only because I know it's true. I don't think that is actually a helpful thing as far as helping you understand, but that's okay. Maybe this is something we don't understand. The x plus 6, you're going to bring that down. Keep the inequality sign pointing the way it's pointing, and then put your 2 to the power of 3 over here. So then you're looking at x plus 6 is greater than or equal to 8. Subtract 6 and you get x needs to be greater than or equal to 2. So there's your domain restriction. That's your domain restriction on the radical. We need to always use values bigger than 2 to ensure that everything under the radical is positive. For the moment, plug into 2 plus 6 is 8, log base 2 of 8 is 3, and 3 minus 3 is 0. So we definitely found our little cutoff value that gives us 0. And to get bigger values of logs, you need bigger numbers in the parentheses, so it would make sense then that x has to be bigger than 2 rather than smaller than 2. And that's literally how I figured out which way this inequality should go, is I found the thing that makes 0. And then I tested a value that was bigger, and it worked. So I know that we need to be 2 or more. If I had tested a value bigger than 2 and I got something negative, then I would know that we don't want to be 2 or more, we want to be 2 or less. And honestly, there's just not shame in that in pre-calculus anymore. We're dealing with much more complicated functions, and so you're not going to necessarily have like the rules memorized. You're instead going to just kind of fall back on a bit of common sense and maybe a little bit of guessing and checking, and that's okay. So anyway, hopefully you agree with me on that. Our domain for the moment appears to be only those values that are bigger than 2 or equal to 2. But wait, there's more. We're supposed to also consider the domain of the inner function. But the domain of our inner function said it would happily take anything greater than -6, remember? So if I intersect all the stuff greater than -6 with all the stuff greater than -2, then being positive 2, all the stuff greater than 2, that's already the more restrictive domain. So the intersection of the two is going to be that. So I don't have any more restrictions. That is my final domain, because the log function, the inner function, didn't have any new restrictions that we had not already accounted for. So there. Are we done? Okay, good. Another one down. 19 minutes and 42 seconds. We're going a little faster now. I'm going to stop and I'm going to do number 4, and they're all going to be separate videos. See you later.